Quality's still really bad. Um, look on my end, I feel like it's still glitching. Oh wait, oh wait, we might be in the clear. Okay, it's looking pretty solid right now. I think we were just hitting a rough patch of internet or something. I think we're good now. Yeah, I think we're good now. Okay, so I'm gonna keep going. I think we're in the clear. So, to reset on this problem, here's the exterior angle, and here's the two interior angles. Um, we got to use a little bit of knowledge here that, okay, I might not know this, it might not be given to me, but I know that this is a straight line, and if this is 50, the angle right here has to be 130. 150 equals 130 plus question mark. Boom. Subtract the 130, we get our question mark of 20. Oh yeah, quality's looking much better right now. It's looking steady. Um, and to just up the ante here, right? What is a quadrilateral? A quadrilateral is essentially two triangles put together. How many degrees are in this triangle? 180. How many degrees are in this triangle? 180. So, how many degrees total are there in a quadrilateral? 360. Simple as that. So that's why we're doing these things together, right? It's not a new topic. It's just like, okay, take this one thing and let's up it just a little bit more. So quadrilaterals have a total of 360 degrees inside of them. So 360 equals 72 plus 108 plus 81 plus question mark. Most of us probably don't even need to write this down. You can just kind of plug it into a calculator and be fine. But I'm going to write it down because this is whether you're doing it in your head or not, this is the correct math. And we're going to want to make sure we all do it correctly. So 99 equals our question mark there. Same idea here. 5x plus 16 plus 102 plus 100 plus 92 equals 360. So 16 plus 102 plus 100 plus 92. So that's 5x plus 310 equals 360. Subtract the 310, you get 50. Divide the 5, you get 10. Super easy lesson. 100 plus 8x plus 8 plus 80 plus 11x plus 1 equals 360, right? Just add up your angles together, set it equal to 360 for a quadrilateral. Add up your angles together, set it equal to 180 for a triangle. But we're doing quadrilateral, so it's 360. So 8x and 11x make 19x, and then 100, 8, 80, and 1. 100 plus 8 plus 80 plus 1 is 189, and that's set equal to 360. Subtract the 189, you get negative 171. Not negative. Why did I say negative? You get 171, and then that is divisible by 19, and you get 9. So I already answered this question. How does the triangle sum theorem relate to the quadrilateral sum theorem? A triangle is 180, whereas a quadrilateral, which is two triangles, gives you 360. All right, because adding up angles for quadrilaterals and triangles isn't all that difficult, we're sprinkling on a little bit more here with isosceles triangles. And an isosceles triangle is a triangle with at least two congruent sides. Congruent meaning equal, so this side is the same as this side. So the left and right are the same, but the base might be different. Or the left and base might be the same, but the right might be different, right? Two out of the three need to be the same. Often they're drawn like this, right? Where the legs are the same and the base is different. That's just how people tend to draw them, but it doesn't necessarily have to be that way. For example, this guy, right? It's turned on its side. So, but lots of people imagine it sort of like base with legs. The congruent sides are called the legs of the triangle, as I was just referring to, and the other side is called the base. So I just used those words before even filling in those blanks, but hopefully that kind of felt natural to you. And the angle formed with the legs is called the um, vertex angle, right here. And the other two angles that have the base as a side are called the base angles. So these two legs come together, as it said here, formed by the legs, and make a vertex angle. And however, this base and leg make that angle. The base and leg make that angle. Those are referred to as the base angles. So, what is so special here? Um, for isosceles triangles have congruent legs and congruent base angles. Okay? So we look at this picture and we go, oh, the legs are the same. Well, as this double arrow suggests, if the legs are the same, well, then therefore the base angles are the same. All right? You can trust that at any point, right? The directions here didn't even say that these were isosceles triangles, okay? We just look at the picture and go, oh, the legs are the same. It's isosceles. And if the legs are the same, then these base angles are the same. So, what is the measure of those base angles? Well, we know that they add up to 180, right? Well, this angle and this angle are the same. So I'm going to use x for both of them, right? This angle is not different, right? I wouldn't call this y, right? Because that would imply that x could be like 50 and y could be 80, right? No, 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 right? They're both the same. They're both x. So x plus x plus 64 equals 180. 2x plus 64 equals 180. Subtract the 64, you get 116. Divide the 2. What is that? I don't want to screw that up. 58. Another way to look at that might be like, okay, like maybe you don't like looking at it in terms of an equation, but just think about it, you know, from just like a logical perspective. If those two angles are the same, what are we saying? There's 180 degrees in the whole thing. Take away 64. Well, the remaining angles, right? This is 64, and the rest has to add up to 116. Well, if the two are the same, you got to split that 116 in half, aka divided by 2, right? That's like the logic. I know this adds to 180. This bit is 64, so the rest of it has to be 116. Well, if those two things are the same, then just split it in half by dividing by 2. This, again, the legs are the same, so therefore the angles are the same. And if those two angles add up to 70, then 70 plus t needs to add up to 180. Well, angle t is 110. That's pretty straightforward, right? It's got to add up to 180 degrees. These two add up to 70, so the rest of it has to be 110. One more time with angles. If the legs are the same, the base angles are the same. So 40 plus 11x minus 18 plus, well, 11x minus 18, because these two angles are identical. Add all three together, and you get 180. So 40 plus 22x minus 36 equals 180. 40 minus 36 is 4. Subtract the 4, you get 176, and 176 divided by 22 is 8. So x is 8. But it looks like it didn't ask us for x, it asked us for angle F. Well, just plug it in, and you'll get it. So 11 times 8 minus 18 is 70. All right, two more quick ones. If the angles are the same, then of course the legs are the same. So set those legs equal to each other. What should I do? Subtract the x, so you get x, and add the 1, you get 5. I'd encourage you to plug it in just to double check that. So 2 times 5 is 10, minus 1 is 9, and 5 plus 4 is 9. Yay! They're equal to each other. If the angles are the same, then the legs are the same. Set those legs equal to each other. Subtract the x, you get 2x. Subtract the 2, you get 4. Divide the 2, you get 2. I would encourage you to plug it in just to double check. 2 plus 6 is 8. And 3 times 2 is 6, plus 2 is 8. Yay, we got 8 on both sides. So over here was 9, and over here is 8. And we did it. Easy lesson, right? Easy, 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 easy. Do not overcomplicate it. I guess this last question I didn't answer. How can you extend the isosceles triangle theorem to an equilateral? How can you extend the isosceles triangle to an equilateral? Well, equilateral means all sides equal. So if an isosceles triangle has these two bases the same, well, then an equilateral triangle has all three angles the same, right? Look at it from this perspective, right? If these legs are the same, then these two angles are the same. Well, the same thing would be true. Oh, well, these legs are the same, so these angles would be the same, right? We're just repeating ourselves saying, oh, these legs, these angles, these legs, these angles, these legs, these angles. So in the end, we're saying all the angles are the same. I zoomed out. Should I zoom in to anything? I'm going to post my announcement for Algebra 2. So did Twitch smartly realize that I ended the stream and then turned around and went live again? Or did it separate the videos? I'm going to guess it probably, yeah, it's separated. That's annoying, but it is what it is. You too. Thank you for coming. Looks like it was split. It's because there's a 17-minute video on my channel. I don't know. We'll see how it ends. All right. Still need to make my announcement here for Algebra 2. All right. We are live doing Algebra doing. Algebra dos. Anybody already here for Algebra 2? All right. I don't know if anyone is here for Algebra 2, but nonetheless, I need to record this so that way people can watch the replay. So, right about here will be the start for Algebra 2. Thank you for watching, live or the replay, whichever. Today we're looking at the graphs of these polynomial functions. So, I wanna try to make today short. My mission is to make today short. We'll see. Let me get rid of this. So, we haven't really looked at these graphs too in particular. Our polynomial functions are, again, functions that, are a little bit longer and messier and whatnot. And we haven't really looked at them all that much. And you can see that, they got some pizzazz to them, right? And how about I, do something like this? They've clearly got some pizzazz to them. Now, we're not gonna perfectly graph these by hand or anything like that. That's not what we're here to do today. What we're here to do today is understand why the graph is doing what it's doing and know when it will cross and why is it, bouncing and going up and down, and why is this graph opening up, and why is this one not going back up? Why does it go down infinitely? That's what we're here to investigate today, okay? So, let's go back to our notes. And we call the whole up situation or down up situation the end behavior. So the end behavior is the trend of the graph on the left/right. All right. Hello. Thank you for coming to watch live. So, what is the degree of a function, right? That is the biggest exponent, okay? So you might have x to the third, x to the fourth, x to the fifth, x to the sixth. Whatever it may be, if it's even, and if the lead coefficient is positive, your graph is going to look like this. It's going to go up, up. Okay? It's going to go up, up. And I'll just show you a couple, right? 2x to the fourth, it goes up, up. 2x to the sixth minus 2x. In the end, it's still going up, up. It's an even degree, and a positive lead coefficient because it's going up. And the second I were to switch these and make them negative, it's now going down, down. So, switching back to the notes, if it's still even, but all of a sudden we make the lead coefficient negative, it's going to go down, down. There might be some weirdness in the middle, but that's not what I'm here to discuss right now. I'm talking about what's happening on the left and right. It's going to go down, down. I'll fill these blanks in a second. So what happens when it's odd? Well, I already showed you an odd one, but here's 2x cubed minus 4x. It's got some wiggle. It's got some pizzazz. It's going up on one side, down on the other. Here's another one, 5x to the fifth minus 4x cubed plus 2x. I said cubed, but I ended up typing squared, whatever. It's going down and up. So that's right, you guessed it. If it's odd, 3, 5, 7, and positive, it's going to go down on the left and up on the right. And if it's odd and negative, I can just as easily switch these to negatives. And all of a sudden it flipped it, and it's starting up and working its way down from left to right. It started up and it's working its way down from left to right. So how do we write this in an official manner? Okay, how do we write this in like an official manner? Well, when we're going to the left, that's negative infinity. And when we're going to the right, that's positive infinity. And when we're going up, that's also infinity. And when we're going down, that's negative infinity, right? As we go up, 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 or down, 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 to the right, to the right, to the right, right? We're used to speaking in terms of infinity. Well, as we go to the left, this means left, right? Y is getting big, right? As we go to the left, Y is getting big. As we go to the right, to positive infinity, Y is also getting big. It's going up. I'm not going to write left up, right up every single time, but I'm just showing you for that first example. On this other one, as we go to the left, instead we're going down, right? And as we go to the right, we're going down. So this arrow means as x is going towards infinity, as it goes to the positive infinity, what is it doing, right? As your graph continues to go to the right, where's your graph going? It's going down, 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 down. So as we go to the right, it's going down, and that's what this is saying. As we go to the right, my function's going up, 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 up. As I go to the left, my function's going down, 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 down. So as I go left, I go down. As I go right, I go up. As I go left, I'm going up in this case. As I go right, I'm going down. So the way I like to think of it is even is symmetrical. Positive, go up. Negative even, go down. It's like goalposts, right? No, it didn't. Where's my just chatting? So my webcam's big. Even is symmetrical. Positive is up, up. Negative is down, down. And then I got to think about how my webcam's flipped. So positive, odd. So odd likes to get bigger or it likes to get smaller, right? So thinking about the flip of my webcam, right? That should look correct for you, right? This is positive because it's getting bigger, right? I'm small over here and gradually getting bigger, and then flip that around, negative. Negative means to get smaller. So I'm starting big and I'm gradually getting smaller, right? That's what I like. That's how I easily remember those. Even positive, up, up. Even negative, down, down. Positive, odd, it just likes to get big. Negative, it likes to get small. So here, with these quick questions, it just asks us to describe the end behavior. So I see that, okay, it's negative with an even degree. So I know it has to be down, down. So and I'm going to write this out maybe twice. The questions are multiple choice on the classwork. So as we go to the left, we're going down. As we go to the right, we're going down. You just have to pick the correct option, right? It's multiple choice, and I've listed all 4. You just have to pick the right one. So I look at this and I go, it's negative with an even degree. Down, down. I look at this and I say it's positive with an odd degree. It's working its way up. So it is positive with an odd degree. So therefore it's working its way up. Okay? So on the left, it's down, but on the right, it's going up. I'm literally just copying what was above, okay? Don't think I'm reinventing the wheel here or anything like that. You've already written it once, hopefully. Maybe you printed this out, right? Or maybe you're just watching. But right, it's the same thing that I had written above. So I look at this. All that matters is that very first term, right? Or the one with the biggest exponent, right? That very first lead term. So this is a 1 and it's odd. So positive, odd, that's literally the exact same thing as what I just did. So CB, right? It's the exact same thing. This one is negative even. Apparently, we couldn't reinvent the wheel here. CA. All right? All that other stuff doesn't matter when you're talking about the end behavior. It might wiggle like a psychopath in between. It might be the craziest graph that you've ever seen. But if it's even and negative, you betcha it's going to be down, down. All right? That's just a fact. There might be a whole bunch of wiggles in the center, but nonetheless, it's going to work its way down. So here's a quick little fun matching set of problems. So I like to focus here on, all right, I see a negative. I see negative, odd. The second I see that it's odd, I know that this function and this function is out. Why? Because odd functions have opposites, right? It's not symmetrical where it's up, up, or down, down. It's going to be different, okay, for odds. So I immediately know these two are out. If it's negative, it's got to work its way down. So this is X. So this one's out now. I see that this is even, so I know that these two are out. Well, I already used that one, but the point is those are going to be out. So it's positive, so it's going to go up, like this guy. So that one's out. This one is positive odd. Well, odd means it can't be any of these symmetrical ones. Positive means it's going to grow. Don't stress about, oh, like, this notation just seems like it's taking a while to write down. It's just about the notation. I'm giving it to you multiple choice style. I want you to think about what it means, right? Positive means growth, right? Negative means decline, that sort of thing. So this is negative even. So I know it can't be either of those because they aren't symmetrical. Well, this one's growing, this one's going down, hence the negative. So that is Z. Hopefully that's making quick sense. Hopefully you're all right with that. One more time. What are we looking at here? This is declining. So I know it's got to have a negative. And it's not symmetrical, so I know it can't be even. It's A. Right? Right? Okay, so I skipped a few things up here at the top. Let's go back. A max versus a min. This is largest. So when we're talking the maximum or minimum of a function, we're talking about the y values. What is the largest y value? So in other words, what's the highest point of the graph? Because these things are bobbing up and down, right? What's the highest point versus what's the lowest point, or smallest, I should say. Max versus min. And then there's something that's called the local versus absolute. So let's just see it in an example, and then it'll really make sense. So you can see that the maxes are going to be where the peaks are. So here and here, right? And the mins are going to be where the valleys are, here and here, right? I hope that makes like 100% sense, all right? The peaks are your maximum points, and your valleys are your lowest, your minimum points. So what I see here is a max at 5 and a max at, I kind of made my point so big I can't tell. It looks like about 2.5, to be honest, or no, 1.5. And then I see a couple of mins at like -1.5 and at -5. So it's kind of symmetrical in a way, right? Sort of, not kind of like a flip, I guess. So which are local, which are absolute? What does this idea mean? Well, to be absolute means like, well, let me make a comparison, right? Well, I'm just trying to think of an easy way to phrase this to help you remember. Local just means like relative to the points around it, it's obviously kind of a maximum, but absolute means literally the biggest one, right? So there are multiple maxes, but the absolute is the biggest one. So up here, I guess I could say absolute is the biggest max. Okay? There can be multiple maximums, but this one is the absolute and this one is local, right? Clearly they both have a peak, right? These are both maximums, but 5 is bigger than 1.5. This is the absolute max. This is the local max. Same idea with a minimum here, okay? This right here is a local, whereas this is an absolute, because this is more negative than this one. You with me? So absolute max at y equals 5, local max at y equals 1.5. Absolute min at y equals -5, but a local min at y equals -1.5. So take a look here. We have a max here and a min here. Well, in this situation, we have a local max at, what is that at about? Honestly, 6, let's just call that 7, okay? At about 7. And then we have a absolute max at y equals 9, right? But what am I getting at here? What am I about to say? Well, this right here is an absolute min. In fact, it's the only minimum, right? It's the only minimum value on this page. You know what I'm saying? I wait a minute. I think I have misspoken. I just realized something. I just misspoke. If you're watching live, I'm sorry. You're watching the replay, I'm sorry. I have misspoke. It just kind of dawned on me. I have misspoke about absolute. Because of something that I blatantly ignored, and that's my fault. This is the struggle with doing it live. My video is not going to be perfect. So these are going to be considered local. These are going to be considered local because it's not literally the biggest point on the graph. That's my bad. It's not literally the biggest point on the graph, right? Because this goes up to infinity. So there is, okay, yeah. So there is no absolute max because it goes on forever. I should I even just tell you what triggered that? My friend from college just texted me, and I don't know what ran through my brain, but he's smart, and I was like, what if he's watching the stream right now and he just texted me that I just said something wrong? He didn't. He texted me a picture of a new car that he just got. But it ran through my brain, and then I was like, wait a minute, I did do something wrong. I just said the wrong thing. So I'm not wrong about the absolute max over here, by the way. And there is no absolute min because it goes on forever. Okay? So these are both local. Over here, though, this literally is the highest point, right? So that definitely is the absolute max. But as I just said, this is going to go down forever. There is no absolute min. So with that being said, there is a local min at y equals -6. Wow. Glad I caught that. Does that make sense to us watching live? Have I corrected my error? Did I explain that well? All right. Well, hopefully the rest of us will be able to say the same. Thank you. I may have made a mistake, but in the end, it is easy to identify these mins and maxes, right? I definitely didn't screw that part up, right? I think it's easy to see the peaks and the valleys, the peaks and the valleys. It's the probably the numbers that matter most, right? I want you to know that these are mins and maxes, and hopefully I managed to correct myself well enough that you'll be able to know that it's local versus absolute. All right. So the last part here, um, when you have something written like so, you know how we have factors, and you might have a factor squared or a factor cubed or something like that. Okay, we've seen things written like this on occasion. This thing right here is called its multiplicity. So don't freaking stress about that fancy word. But you're going to see stuff written down like that. And when you see stuff written down like that, if n is odd, okay, so you might see graphs that look like this. You might see graphs that look like this. You see how the graph crossed through? It went sliced right through, right through, right through. Here it went right through and then bounced and went back up, right? We're focusing on where it's crossing or touching the x-axis. Well, if your multiplicity is odd, it crosses. If your multiplicity is even, it bounces, as I like to say. Let's see it in action. Let's see it in action. We know that because this function has been pre-factored for us. You're welcome, right? We've been doing lots of factoring. This function is pre-factored. So there is a 0 at -2. There is a 0 at -1. And there is a 0 at 4. This has a multiplicity of 2, so it bounces. This has a multiplicity of 1, so it crosses. Before I draw it, though, what is the degree of this polynomial? It is a 4th degree polynomial. 1, 2, 3, 4, right? If I were to multiply this all back together, what would be the biggest exponent on the x? X to the 1, 2, 3, 4, right? Because x squared times x again, that's x cubed, times x again, that's x to the 4th. You see what I'm getting at? This is x squared times x again, that's x cubed, times x again, that's x to the 4th. So I know that my graph looks something like this, right? It has to go up, up. So, because we know that it bounces at -2, but does it bounce like this, or does it bounce like this? Well, the answer is the second one, right? Because it has to go up. So, bounce, cross, cross. Let me plot it into Desmos really, really quick. X plus 2 squared times x plus 1. I Desmos sometime? Take a look at this. See that? the function's a lot longer than what I drew, but nonetheless, it comes down and bounces at 2, crosses at -1, comes down, and then goes back up and crosses at 4. So, honestly, in my drawing, I should have like this. Saying? So we have a 0 at -3. We have a 0 at 0. And we have a 0 at 2. It's going to bounce, cross, bounce. And what is the degree of this function? 1, 2, 3, 4, 5. It's a 5th degree polynomial and it's negative. So it has to look something like that. It's got to work its way down. So that means when we bounce at the first thing, we're coming down and bouncing up, and then crossing, and then bouncing and coming down. You with me on that? I'm just following. 2 means bounce, 1 means cross. Think about what it could have looked like this, right? It could have looked like bounce, cross, bounce. But that would have been positive. That would have been if it were going up. Ours is negative. It's going down. So bounce, cross, bounce goes down. You can always check this with Desmos, right? All right, this is the last set of problems right here. I'm actually not going to well, we can do 8 because it's multiple choice, but I'm not going to do 7. Write the general factorization in factored form. So this is telling you to look at the graph and come up with the factored form that we just had right there. So to look at the graph and come up with the equation. So what do we need to do? We need to identify the zeros and then think, okay, it's crossing here, bouncing here. Yeah, York, I'll be able to help you out in just a second. So it's crossing and bouncing. So that is crossing at -6 and bouncing at -4. The factor is x plus 6. Please don't forget to take the opposite. The factor is plus 4, all right? It's crossing, so it's just a 1, right? Or nothing, you don't need to write it at all. And it's bouncing, so it's 2. The only question is, do we need to account for a negative or anything like that? Well, this thing is working its way down. This is a negative function, so let's slap a negative. So I identified the zeros, wrote the factors. Crossing means odd, bouncing means even. Let's do it again. The zeros are right there, which is at -3, so plus 3, -1, so plus 1, and -2, so minus 2. +2, so it's at -2. I see cross, cross, cross. Easy. I'm like done. I'm done. Is it negative? Well, this thing's going up, so it's going to stay positive. Boom. I'm done. All right, the last bit, the last multiple choice question, it's literally the same thing over again, one more time to nail this in our heads here. This is a positive function, so I know that it's not going to be down, down. It's going to bounce at -2. That's the most distinguishing thing that I can see here, right? So which ones are bouncing at -2? Not this one, right? It crossed. That's no good. This one crossed at -2. That one's no good. This one better have bounced. Yep, it did. And it's also crossing and crossing, just like it's supposed to. So B's the right answer. York, you want to type up your problem? I can answer it. And also, those of us watching live, you guys got any questions on what I did here? Any of these guys? Yeah, I didn't think that was too bad either. I tried to make the classwork pretty straightforward on these. Not that I try to make it convoluted ever, but um, I don't want us to get too overwhelmed with the graphs, right? End behavior, one big thing, and then like the bouncing and crossing's the other big thing. I'm ashamed that I messed up the local and local and absolute, but I'm glad I caught myself before I went and freaking posted this video. You guys are interested? He's got a Honda Civic Black. You too. Thank you for watching. Yeah, yeah, give me a question. You must not have heard me. Yeah, you can. I asked, asked you to type it in the chat. I thought you left me. Your question? Okay, gotcha. That's pretty. That's very manageable for me. It's a pretty easy problem. So your slope-intercept form is y equals mx plus b, where this is your y-intercept and this is your slope. If you have a t-chart, do you happen to have a point where x is 0 and then there's a number? If you do, that is your y-intercept, right? Let's say it was a 6. Well, then you would plot that point at 4, 5, 0, comma 6, right? And that's your y-intercept. Do you happen to have that, York? So I would know that much. Right? I don't know the slope yet, but I would know that that's 6. Well then, in that case, York, have you learned point slope form? Point slope form is oh, I'm blanking. What is point slope form? How am I not remembering point slope form? Oh, wait. Yeah, I remember now. Y minus y1 equals m times x minus x1. You've learned point slope form? Okay. So then we know what to do. All right, so find the slope. Rise over run. So x2 minus x, sorry, not x. y2 minus y1 over x2 minus x1, right? So I'll use your point -310 and -1,4. Let's find the slope. So y minus y over x minus x. So I get -6 over 2. So my slope is -3. Which makes sense because we're going down, right? -3, 10, and then -1, 4. We're working our way down, right? So my slope is -3. And then point slope form. So y minus, just pick a random point. So I'll use your -1. So y minus -1 equals slope. We just solved for it. Times x minus x1. Oops. Sorry. That's 4. The x value is -1. You with me? Sorry, I'm writing a little sloppy. I can clean it up here at the end. So we found our slope. I hope you were with me on that. And now I'm using this as my point. So y minus y1, 4, equals your slope that we just found, x minus x1. Well, that's the other x value. What up? With the wahoo emotes. So then y minus 4 equals -3x, distributing, times, so -1 becomes +1, and -3 times +1 is -3. And slope-intercept form, just go ahead and add that 4 over. Trying to play, Noah? I haven't even downloaded it yet. Is it a quick download? Does that make sense, York? Before you leave me, York, do you have a question? Cool beans, York. All right, well, glad we were able to answer that viewer's question. Yeah, no, that was York isn't even one of my students. It was just what a guy or girl. What a legend. All right. Well, with that being said, I'm ending the stream.